Okay, so let's resume the activities of the day. So it's my great pleasure to introduce our third speaker, Paulo Orenstein, also here from IMPA. Paulo obtained his PhD in statistics at Stanford University in 2019 and then came to IMPA in 2020. His research focuses on the interplay between statistics, probability, and computation. And even though he's been here for only 2 years, he's been one of the main driving forces of IMPA's Centropy. So today he's going to tell us about split conformal prediction and its extensions to non-exchangeable data.
Thank you so much, Carolina. So it's a pleasure to be here today, and it's a pleasure to have been here for the last 2 years. So what I'm about to talk about is joint work with some amazing people here at IMPA, including Roberto, Thiago, and João Vitor. So the agenda for today is as follows. First, I want to give some motivation for the issue of uncertainty quantification. That is, I want to give a very concrete example in which making good predictions about the future is just not enough. We're interested in ascertaining how sure we can be of these predictions. So this is essentially the difference between a doctor telling you that she thinks you're cured, she's 65% sure, in which case you might as well go do exams for the rest of your life to make sure everything is okay. And the doctor telling you that, she thinks you're cured, she's 99.99% sure, you can just go home and relax. So measuring this uncertainty is fundamental. Now, the way we usually, or one of the main ways to do this in statistical models, is to assume a very strong parametric form, something like Gaussian processes. However, this sometimes comes at the expense of prediction accuracy. So the approach we want to take here today is different. We want to develop a way to know the predictive uncertainty of any statistical or machine learning method, whichever method it is. We don't want to have to tweak the method. So this is a pretty tall order. We're not assuming much, but this is one of the main driving forces for this modern statistical field of conformal prediction. So the idea here is to try to give these valid predictive intervals for any predictive method. And it works in full generality. There's essentially one strong hypothesis that's made, which is that the data that you're considering is exchangeable. So if that doesn't mean anything to you, it's fine for now if you just think of exchangeable data as independent and identically distributed data, okay? IID data. So there are at least 2 reasons why we might want to extend this technology beyond IID data. The first, of course, is that there are many situations in life where data is just not IID. So if you have a time series, or if you have spatial data, then this technology wouldn't work. But a second and more fundamental reason is that even if you think your data is IID, once you go out into the real world and you try to do things, well, things are approximately IID. And so to what extent can we still use this methodology if your data is approximately IID or approximately exchangeable? So this is the content of our work. I want to discuss a little bit about the results that we obtain. And the main message here is that things are just fine. So it's good news. That is, even if there is some dependence in the data, the methods, these really nice methods that were created for exchangeable data still work pretty well. And then I want to conclude discussing some further directions. So as I said, I want to start with some motivation. Okay, so I'm going to ask you to look at me for a second because I want to tell you a story. So the story begins last year when some doctors at DASA, this is one of the largest clinical diagnostics company in the world, came to us at Centropy, IMPA's Center for Projects and Innovation, with a really interesting project in fetal medicine. What they were interested in is they wanted to know if we could accurately and quickly measure the amount of amniotic fluid in a pregnant patient's womb. So the amniotic fluid is the fluid that surrounds the fetus. And doing this is really important for them because it's a key indicator for the health of the pregnancy. So if it's too little or a lot of amniotic fluid that you have, things are not good. So how do they do this today? Well, if you're pregnant, the first thing you'll do is you're going to get an ultrasound, out of which the doctors get a pretty rough understanding of what's going on. And if things look fine, they're just going to really guess. They're going to look at the ultrasound, and they're going to say, like, well, you know, the fetus is almost like a block, and your belly is like this, blah, blah, blah. It's OK. It's good. Now, if there's anything dangerous going on, however, then this is not enough. So you're referred to an MRI. An MRI is a magnetic resonance imaging. So you can think of it as a sequence of slices that goes from the pregnant patient's navel all the way to the spine, like a sequence of slices of images where you can see what's going on each slice. Then you do this exam. This exam gets sent to a specialist, like a technician. And then this medical specialist will go through every one of these slices, hundreds of slices, I should say, painstakingly drawing out what's the amniotic fluid and what's not. And after all of this is done, they can just count the pixels in each slice that correspond to the fluid, or more appropriately, the voxels. But then you get an estimate for the volume. This is how it's done today. This process takes many hours, if not days. At which point, the pregnancy might have changed altogether. Days is just too long. So the question was, can you do it faster? So I want to give you a rough idea of how this process looks. I want to show you a video. What you're going to see in this video in the background is an MRI exam as a sequence of slices. So it will be a video. And for every slice, doctor has drawn out what's the fluid and what's the fetus. And so you're just going to see the fetus pop out of the exam. Okay, so this is the MRI. And so for every slice, we're drawing out where the fetus is. And so once the MRI exam is gone, this is what you have left. And in blue, you have the fluid surrounding the fetus. Okay, so there goes the fetus. We had to estimate the volume of this weird object. Okay, important for pregnancies. So how to do this? Okay, so to recap, we were approached by these guys at DASA, Dr. Aaron Werner, saying, given fetal MRIs, could you estimate the amount of amniotic fluid? So this is important, as I said, mainly because it's a leading indicator of the health of the pregnancy. But today, the ways we do it are just either imprecise or too slow. So our goal was, doing this accurately and fast. So how to go about this? Well, our idea was to just, do what a human, what the doctor would do, which is look at every one of these slices, figure out where's the fluid, and then count the voxels. So that's what we did. But instead of using a human, of course, we used a machine. So we used something called a UNet. This won't matter too much for today, but it's a deep neural network, so it's a model with millions of parameters. But the point is, it works really well. And after all this work is done, we get something like 5-second time to get an estimate. This is really fast, right? This is, before you leave the MRI machine, we already have a number ready for you. And with really good accuracy, so it's 92% dice accuracy. So rather than going into detail of what I mean by 92% dice accuracy, I want to show it to you. So here's a second video. There we go. Here, you're going to see a sequence of exams of MRIs, and I'm going to compare two things. The predictions from our algorithm versus a human, or a doctor, segmenting everything. The doctor took many hours, days, etc., and this algorithm took 5 seconds. So whenever you see pink, it's because we agree on where's the fluid. Whenever you see blue, it's because our algorithm predicted there was, or did not predict there was a fluid at a pixel where the human thought there was fluid. And if you see red, it's the opposite. That is, we're predicting, there's fluid over there, and there isn't. Okay? So ideally, you'd see lots of pink and not a lot of red or blue. And hopefully, you agree that that is generally the case. You see some blue, and you see some red. They don't matter that much here, because they're usually around the borders. And the borders are fine for two reasons. The first reason is that even humans cannot agree on the borders, right? Where does the fetus end and where does the liquid begin? Hard. The second reason is we're trying to estimate volumes, right? So if we're making mistakes on each slice, a little bit too much or just too little, they sort of cancel each other out, and we still get a pretty accurate volume estimation. In fact, in terms of volume estimation, we can see here, every point here is one exam. So these are test exams. So I didn't train on this data, right? So this is all fair. So these are test exams. On the x-axis, you see the prediction from our algorithm in liters. And the y-axis is the target volume. That is the volume that the human computed. And so if all goes well, we would have something concentrated along the 45-degree line, which is, agreement. And I guess you'll agree with me that this looks, pretty good. It looks pretty good, right? It looks pretty good to the extent that you could wonder, well, maybe you could do what I showed you in the first video, right? You just get, the image and you subtract away what the fluid, is, and you should have the fetus left. And in fact, I'm lucky enough to have Jorge, my colleague at Centropy, who was kind enough to actually do this. So he actually printed, so this is a 3D printing of what's left of the womb once we remove our predictions for the amniotic fluid. So this looks like a baby, right? I mean, or it looks to me, I don't know. So it's sort of like case closed, right? We can do this fast and couldn't do it well. But then the question is, can we really trust these results? Like, really? And there's a reason why I ask this, which is in medicine, quantifying the uncertainty is absolutely fundamental. In the following sense, well, there's a world of a difference if a doctor tells you that, well, my best guess is that you have, 2.8 liters in your womb, which is good. But if he or she had to be 90% sure, she would say, well, I'm 90% sure that the true amount of volume is between 2.72 and 2.88. Great, healthy pregnancy, all good. Or, well, I'm 90% sure that the true volume is between 1.9 and 3.7. And here, things could be bad, right? You cannot exclude the possibility that something bad is going on. So it's in this sense that I mean that I'd like to quantify the uncertainty. So how can we provide valid predictive intervals for any black box prediction method? In the sense that, the UNets, whatever they were working fine. I don't want to mess with them. Could I still have these valid intervals for the volume? Okay, so this is what the field of conformal prediction is about. So if I turn this a little bit into some math, I'm going to rephrase that question as, given data, x, y, yi, to train any prediction method mu hat and any level alpha in 0, 1, can we construct a prediction set, C1 minus alpha of x, such that for any new point that I haven't observed, xn plus 1, yn plus 1, I can guarantee that the probability that this unseen yn plus 1 is in my prediction set is bigger than 1 minus alpha. So in our example, what does this mean? Well, in our example, xi is an MRI exam. Yi is the fluid volume that I want to predict. Mu hat is this unet. And C, what I'm interested in, is this rule that will specify a volume interval, that is, the interval for the volume, given this exam, this MRI exam xi. Okay? And I want to do this with this really nice probabilistic guarantee. Okay, so this is the problem that we're trying to solve. So the field of conformal prediction was proposed by Vladimir Vovok in 2005, not that long ago, but the idea started picking up steam recently. Vovok was one of Kolmogorov's last students. The idea is to give you valid predictive sets for any level alpha and any model mu hat. Whoops. There are many, many, many extensions of this idea. It works for regression, where we're trying to predict a real number. It works for classification, where we're trying to predict a category. I'm going to focus on the regression case today, but that's just for convenience. And this idea has lots of different incarnations. There's this fundamental idea. You could use it in many ways. We're going to look at one called split conformal prediction. And the name split will come into play, the word split soon enough. And this works pretty generally with one basic assumption. As I've mentioned, we need the data to be exchangeable. So this is implied by IID. But what I mean by exchangeable data is that if you get your x1, y1, x2, y2, x3, y3, blah, 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 xn, yn, the order at which they appear doesn't really matter. So they are exchangeable in this sense. So you can think of it as the CDF of your data is just symmetric in the arguments. OK. Sorry. How do we create this interval C, the set C? So this is when I want to tell you about this algorithm for creating C. It goes like this. The first thing we'll do is we're going to split our data into 3 parts. We're actually going to partition the data. So I'm going to have some training data, so XIYI, some calibration data, XJYJ, and some test data, XKYK. So I'm going to try to use different indices for the different sets, so it's just easier for us to follow along what's going on. So I will be for train, J for calibration, and K for test. And the idea here is that we're going to use this training data to train our prediction method, let's say the UNet. We're going to use the calibration data to find this rule C, and we're going to use this test data to see how well we're doing. OK, so once I've partitioned the data, second step is I'm going to train my predictive method. So this is just a function that receives an x and predicts a y. And after that, I will just look at discrepancy scores. So these are functions as hats that take a value in x and y and spit out something in r. So you can think of these as measures of error, how well your predictions are doing. So one example to keep in mind is the L1 error. So you can just think of S hat, the score of x, y, being the difference between your prediction mu hat of x and what happens y in absolute value. So far, I haven't used my calibration data. I'm going to use it now. So what I'm going to do is define S hat j to be my score applied to my calibration data xj, yj. And I'm going to look at q hat 1 minus alpha, which is the empirical quantile of my calibrated scores. Okay, so this formula is more complicated than it needs to be. Let me tell you what's going on there. Suppose you have your scores S hat j, so they're all here, let's say. Let's order them, okay, from smallest to biggest. They're all in R. And let's say alpha is 0.1, so I'm trying to find the 90th quantile, empirical quantile. So this is the value, the smallest value in my data, such that I have 90% of my data below it. Okay, that's what this formula is asking for. So it's something that's pretty intuitive. And once that's done, I'm going to just define my prediction set, C1 minus alpha of x, as the set of y's such that the score given my x applied to this y is less than the empirical quantile that I calculated, nudged by a little 1 plus 1 over n cal factor. Okay, that's it. This is the rule. Okay, so this is an algorithm you can follow. I'm going to turn the lights back on so we go through these things once more for our specific example. So for us, X is our MRI exams, the Y's are the volumes. So we have this data for many, many patients. We're going to split it into 3 groups: the training group, the calibration group, and the test group. We're going to train a prediction method on our training data. Then we're going to pick a discrepancy score. Let's say we keep the L1 error here. We're going to find this 1 minus alpha quantile defined this way. Or actually, we're going to find the 1 plus 1 over n cal times 1 minus alpha quantile. Okay? When we apply these discrepancy scores on my calibrated data, and then I have this rule such that if a new patient comes along and she brings her exam, I can just get the exam and say, how sure do you want to be? Well, I want to be 90% sure. Okay, well, if you want to be 90% sure, given this exam, I'm going to say it's between 2.7 and 2.9. Okay, this is what's going on here. So it's an easy rule to follow along, but the question is, why should you do it? That seems arbitrary. So let me tell you of a nice result. Whoa, okay. So it has to do with marginal coverage in the following sense. Given exchangeable data, xi, yi, and a level 1 minus alpha, I'm going to consider the calibrated quantile that we've just defined and take C1 minus alpha to be what we just talked about. Okay, same as before. Then I can guarantee for any single test data point that I haven't seen yet, it's true that the probability that the true volume, or yk, is in my set, C1 minus alpha, is bigger than 1 minus alpha. So this gives us a lower bound. And if the S hat J's are almost surely distinct, I also have an upper bound. So I want to give you a sketch of this proof, so it's clear. It seems very magical. It seemed to me, at least, because honestly, there are almost no hypotheses here. So it's pretty weird. There's really one hypothesis, which is that the data is exchangeable, but that doesn't seem enough to give such a nice result. So here's a sketch of the proof. Since the data is exchangeable, the S hat J's are also exchangeable. So you can trust me on this one, but it's not that hard to see. And so let's consider the 1 minus alpha quantile, not of just the S hat J's, but of the S hat J's and the S hat K. That is, the score applied to my test point. Okay? If that's the case, if I look at it, if I find a 1 minus alpha empirical quantile of calibrated data plus my test data, because the data is exchangeable and the order doesn't really matter, I know by the definition of the quantile that, let's say, 90% of the data should be below my 90th quantile, right? So it just has to be, by definition, that the probability that my S hat K is below my quantile is 1 minus alpha. Well, why isn't this enough? Well, this isn't enough because we have to construct this rule C1 minus alpha without looking at S hat K, right? This is cheating. This is, I have to use only my calibration data. But here's the trick. I don't really need it. And this is a cute little idea. Even though you can't use S hat K for the quantile, there are two equivalent events here. The event that S hat K is bigger than the quantile calculated on my calibration data and my point S hat K. So the event that I have my quantile and S hat K is bigger than that quantile means that the value of the quantile is irrelevant. I can just make it infinity, right? The quantile will stay the same. So I might as well just assume that S hat K is infinite and these events are the same. Okay, well, why is this really good? Because now I don't really need my S hat K anymore. And then, in fact, if I look at this probability, the probability that S hat K is less than this slightly increased quantile on just the S hat J's, that is in my calibration data, well, this extra fudge here comes from the fact that I can just it's easy to see that I can just rewrite this adding an infinity here. So this is a point that's necessarily above the quantile, right? It's infinity. So this guy here is the same as this guy here. And now things are really good because we know that this event is the opposite of this event. And because this is equivalent to this. And we know that S hat K being smaller than this happens with probability bigger than 1 minus alpha. So it's a nice chain of arguments to show that that's all you need to have this guarantee here. Okay. Well, is this all I get? Not really, right? Because if you're a doctor, you don't really care only about the next patient that'll come along. Maybe you care about all of the patients that'll come in tomorrow. So can I say something about an entire set of points, not just one? And sure, yeah, you can. It happens that if the data is IID, so no longer exchangeable, now I really need IID. If the data is IID, then for any epsilon, there exists a constant such that With extremely high probability, I can control, let's say, very close to 1, the average of the indicators of yk being in my set is bigger than 1 minus alpha minus the penalty epsilon. Okay, so what this means is that empirically over my test set, my confidence or my predictive set C1 minus alpha approximates the 1 minus alpha quantile. There's a penalty epsilon here, but again, whatever. You could also care not just about everybody that will come tomorrow. Maybe you care about specific subset of the population. So maybe you're worried about obese patients or people with some pre-existing condition, whatever. Do I still have a guarantee if I condition on these results on some data? And again, yes, if your data is IID and there's a set calligraphic A which has finite VC dimension, whatever that is, then for any A in this set where the probability that xk in A is not too small, again, I'm being, of course, vague here, then it still holds that the probability that yk is in this set conditioned on xk being in A is bigger than 1 minus alpha minus epsilon. So what this is telling us is this technique of split conformal prediction can guarantee coverage even if I'm conditioning on some events. Okay. What does this tell us? Well, first of all, that we have this tool, this conformal prediction tool, which is very general. I'm getting valid coverage and these finite sample statistical guarantees by not asking for much. It works with any exchangeable data, any model you had. It could be a UNet, it could be a linear regression, it could be whatever. You pick your favorite model. It's simple to implement. This is important. It's computationally cheap, so it's not very hard for someone to run this algorithm. And there are further degrees of generality here, actually. So I didn't mention much about the discrepancy score. How do you choose this S-hat function? And I ask you to think of it as a measure of error. Well, you can pick your favorite measure of error according to your problem. So it could be the residuals, it could be the conditional likelihood. It can even be a conformalized quantile. So we're free here to pick basically what we want. And in fact, all of this theory works more broadly than I'm telling you in the sense that it also works, for example, in higher dimensions. So what this means in our case is, remember, we were looking at every single slice and segmenting it, right? Well, maybe you want an upper region and a lower region that with some high probability cover the true segmentation that the medical specialists will make. So even in this case, this theory extends and we can actually say something meaningful there. So we can draw these upper and lower masks. So once that's done, we can go back to our friends, the doctors. And what we did, in fact, was to write a computer interface for them to just load in an MRI exam, a fetal MRI, press a button, and get our estimate for the amniotic fluid, which is here on the right. And what they also get is, on this red box here, our best estimate for the amount of fluid there is, and a predictive interval. So we say, well, at the 90% confidence, let's say it's between 603 and 777. And so this is useful for doctors, right? Well, for many reasons, this gives doctors some power, right, to say, what's the level at which they want to be sort of alerted that something bad is going on. It also gives them an idea of how certain the algorithm is that we're right? If it's really concentrated, then we know we're doing well. In fact, if we go back to this image, what we can now do with all the math that we've talked about is, for every one of these points, we can get predictive intervals, right? We can say, this is our prediction, and we're 90% confidence it's between this and that, and that's actually what you get. So this is going back to that example, and these are true confidence or predictive intervals. And what you see, if I paint them in blue, whenever they actually have the true value, the 45-degree line cutting the interval, what you see is actually, in most cases, you do get the target volume inside the interval. So these intervals were run at the 90% level. So this will be true for the whole talk today. I'm always thinking of 1 minus alpha as 0.9. And here you have a couple of red little intervals where we don't cover, and they do happen. So we're covering at, I think, 92%. So it's really, good. And also a concern that you could have is that, well, maybe our intervals are very large. And that's really not the case here, right? You see these are pretty reasonable. I see an exam that's like 2.3, and I say, well, it's between 2.2 and 2.4 or something like that, 2.5. So these are useful. That's my point. So again, it seems case closed, right? We are going back to the doctors. We're giving them this fast algorithm. It's accurate, and we have some uncertainty quantification built in. End of story, right? Well, kind of, because we have this really important assumption here, right, which is exchangeability. And by the way, I sort of proved that theorem with my hands, by saying like, well, it's exchangeable. This is really important, right? If things are not exchangeable, the theory breaks down. And it's not that it breaks down nicely, it's just the theorem doesn't hold anymore. And so this is a problem, right? If we're putting the lives of fetuses and well, not in our algorithms, I guess, then we might as well make sure that this holds, even if we don't have exchangeability. If we have something close to exchangeability, what happens there? If we're targeting a 90% level and the data is not exchangeable, are we getting something that's 88%? It's as if we had an 88% level. Or are we getting something that's like 52%, much worse? So we need a theory here, right, to help us deploy these sorts of algorithms in the real world. So this is what our work is about. So extending this idea of conformal prediction beyond exchangeability has been quite a hot topic. So yeah, sure, let me mention this. Well, the reason why we care is that there could be some dependency across the exams, right? So in our case, for example, I don't know, maybe pregnant patients are now taking supplements they weren't taking last year, and so the exams all have the different, so there's a temporal effect here. Or maybe pregnant siblings go to the same doctor and they have some genetic component. So who knows? I don't know. Maybe is it fair to assume exchangeability? So that's the point. Okay, so there's been a lot of interest in dealing with dependence here. So for example, there's been some work in dealing with distributional drift, where the distribution of your data is changing. That's not so much our focus. Our focus will be on rebuilding this theory without exchangeability. So how are we going to do this? The intuition is as follows. We're going to look at how our data cumulative distribution function, our CDF, concentrates if we do away with exchangeability and use some loser conditions. And what you can imagine could happen is, well, if the data is exchangeable, this is my interval. But if it's approximately exchangeable, maybe I have to increase it by a little bit, right? And that will be enough. So the question is, what is this a little bit? Well, in our case, so the idea is, well, instead of using the set at C1 minus alpha, we can use the set at some level C1 minus alpha plus eta, and this will achieve the level 1 minus alpha. But then if that's the case, we can just rewrite alpha here in this way to get the probability, just use the same confidence as before, but your probabilistic guarantees are getting hurt a little bit. And we need to quantify this a little bit. This is the eta, which is the penalty that's due to non-exchangeability. So the tools we're going to use for this are concentration inequalities and some decoupling properties of the data. So here we go. To be able to tell you the results in closed form, I'm going to make some assumptions on the data. these assumptions are not strictly needed, but they'll help me give you concrete numbers and true simulations. So here are the assumptions I'm going to make. First, I'm going to assume that the data is stationary. This means that if I look at my data from time t1 to time t2, and I move it along a block to time t1 plus m, t2 plus m, it's the same distribution. And the second thing that I'm going to assume is that it's beta mixing. And what I mean by this is, if you look at the beta mixing coefficient, which is this beta A, this is measuring the distance between two distributions in total variation. First is, if I just look at my data from time minus infinity to 0, and then from time A to plus infinity, right? So there's a block of size A that I'm keeping apart. So there's this distribution, and there's a distribution where these two things are completely independent. Okay? So this beta mixing coefficient is measuring, let's say, how close to independence I am if I take a block of size A out. I should say I'm thinking of these things in terms of time now, because the time series is a natural, non-exchangeable thing to think about. So, but it works generally. So it is beta mixing if this coefficient is going to 0 as A goes to infinity. So if the blocks are further and further apart, things actually become independent. What this means is I'm asking my data to be time invariant and asymptotically independent. So and beta mixing is the notion of asymptotic independence that I'm asking. Well, what are some examples that still fit these categories? Well, there are broad classes of Markov chains, finite sample ergodic Markov chains, renewal processes, autoregressive processes. So it's still a pretty rich class for many, many models we care about. And the main theoretical tool we're going to use here is something called the blocking technique. I'm not going to talk too much about it. I'm happy to talk about it later. So this was developed by Bin Yu in 1994. So what do we get? First, we can actually recover marginal coverage in the following way. Suppose that xiyi is stationary beta mixing, given alpha and some delta cal that's bigger than 0 for any point in my test set k. The probability that yk is in C1 minus alpha is bigger than 1 minus alpha minus eta, where eta is epsilon cal plus epsilon train plus delta cal. So delta cal is something I pick. Epsilon train is this beta mixing coefficient at this point in time. And epsilon cal, I'll tell you who it is in a second. We also get empirical coverage. That is, suppose that my data is stationary beta mixing given alpha and delta cal and delta test, then the probability that the average indicator that yk is in my set is bigger than 1 minus alpha minus eta can be controlled and made close to 1. Okay? Where eta is epsilon cal and epsilon test, or epsilon cal plus epsilon test. Okay, so let me tell you who epsilon cal and epsilon test is. So it's not pretty. let me foreshadow with this. So I'm going to show in the next slide the formula for epsilon cal and epsilon test. And the point is not very much that you understand what's going on, is that you trust me that we know what we're talking about. And also that if n goes to infinity, everything is good. So without further ado, here's how you define epsilon cal and epsilon test. These are the last two lines here. It's honest math. And we can say something, this is, finite simple, there's n here. M basically, it has to do with n. So these things go to 0, et cetera. All's good. And we can give you hard numbers. OK, that's enough of weird math. We can also recover some conditional results, by which I mean, in terms of the marginal coverage, suppose that xi, yi is stationary beta mixing, given alpha in 0, 1, and delta cal that's positive. For any point in my test set, and A in this calligraphic A with VC dimension D, such that the probability that xk is in A is bigger than some gamma, then the probability that yk is in my set, condition on A, condition on xk being in A, is bigger than 1 minus alpha minus eta, where eta is some epsilon cal plus epsilon test. And we also have an empirical coverage version. So suppose that my data is stationary beta mixing, given alpha, delta cal, delta test, and some A, then basically the indicator of yk being in my set gets very close to 1 minus alpha with a probability that I can control, where eta again is epsilon cal plus epsilon test. I again have to tell you who they are, and again I'm going to try to do this quickly so you don't notice how the math goes very much, but I'm happy to talk about this. So this is epsilon cal and epsilon test. Okay, so we control these quantities. We know what they are. But rather than try to convince you that this is reasonable with formulas, I want to show you some examples. So here's a first application. This is an autoregressive process. So for every 11 points in my autoregressive process of order 1, I'm going to try to predict the 12th point. So I'm going to get this interval via split conformal quantile regression, by which I mean the score is that conformalized quantile. This doesn't matter very much, but I'm defining one of the ways to get my score. And this is basically what you get over 1,000 repetitions. So these are 5 different models that I'm using to predict the point: gradient boosting, k-nearest neighbors, linear regression, neural network, and a random forest. The x-axis here is the autoregressive coefficient. So when it's 0, the data is IID. And I'm making it closer and closer to 1. So the data is becoming less and, at this point, it'll basically cease to be stationary. So the closer it is to 1, the worse things are in terms of how non-exchangeable, in a way, the data is getting. And the y-axis is the marginal coverage averaged over, I think, 1,000 simulations. And what's very striking here is, well, if we're targeting the 90th level, this is the dashed line, and you can see that generally, this is pretty good, even if I'm increasing my coefficient, even if I make it pretty extreme, like 0.8, 0.85, 0.9. In all of these cases, it's still pretty much very close to the level that I wanted. Of course, once it gets to 1, things start getting worse. Well, is it horribly worse? No, not really. I mean, it's worse, but it's 0.8. So in the worst case, I guess it's 0.8. So we have this method. We're assuming the data is exchangeable. The data is not. We're asking for a 0.9 level, and we're getting a 0.8. That's not great. But what's really good here is if you're a practitioner and you have an AR1 data with coefficient 1, you'd know. There's no chance here that you'd assume your data is IID and it's not. At this point, I'm okay. This is the doctor's fault. Like they should know better. So it's very clear that the data is not IID. If it's a little IID, things are still good. So this is simulated data. So let me give you a real data example. So this is a time series with spot exchange rate from euro to dollar. And I'm going to do the same thing as before. I have 11 points. I'm going to predict the 12th, and I'm going to do this with boosting. I'm going to train on 1,000 points, calibrate on 500, and test on the following point. And again, I'm going to get the predictive set. That is my confidence or my predictive interval with split conformal quantile regression. And this is what it looks like. So the x-axis here are the days in 2021. The y-axis is the marginal coverage, and this is the time series for euro to dollar exchange rate. So what you see is, so we're targeting the 90% level. Well, it's not 90%. It usually undercovers, right? It's usually below. But it's not that far below, right? So this is 0.88. Right? So that's pretty good. And in fact, if you look at the average over the entire year, we were targeting 0.9 and we got 0.895. That's good. That's good. I'm comfortable with this. And let me give you one final example, which has to do with, rather than looking at the marginal coverage, I want to look at the empirical coverage. And here, we're going to have a 2-state hidden Markov model. So basically, there are 2 states. With some probability, you stay still. With some probability, you move. And then we add some Gaussian noise. So your data is in R. We're again going to use gradient boosting with 1,000 training points. But we're going to use 15,000 calibration points and 15,000 test points. And then we're going to repeat this thing 1,000 times to look at the empirical coverage. That is, whether it's true that the average of the indicator that the yk on my set is in C1 minus alpha, or this is close to 1 minus alpha. And this is what you get. So on the x-axis, you have this dependence factor, sort of the probability that you stay still in your Markov chain. And the y-axis is the coverage. So we're targeting 0.9. Again, so this data is dependent and getting more and more dependent as we roll along here. What you see in the dark blue is the theoretical bound that we have, and it's getting more and more pessimistic as the data becomes more dependent. Still, surprisingly, to me at least, the empirical coverage seems very much concentrated around 0.9. And if we went much further beyond 0.7, at some point this would break. But it seems really robust, and therefore, to my taste at least, ready for action and for doctors to use. Okay, so let me conclude. Uncertainty quantification is crucial for the deployment of statistical and machine learning systems. Conformal prediction is this nice set of tools that gives you marginal, empirical, and conditional coverage. And they usually require a little bit, just honestly, not a lot beyond exchangeability. And what our work tries to do is, make sure that even that can be, relaxed. And finally, I didn't mention a lot of extensions that we have in our work. So it works even if the data is not stationary. The analysis we did works if the data is not stationary. It works if we're looking at some of these other incarnations beyond split CP, some other versions of conformal prediction, such as rank one out and risk controlling prediction sets. And finally, to me, this is a really nice marriage of theory and applied work, where the theory is really needed. The applied work really has some impact. And in as much as we're looking back and celebrating the last 70 years that IMPA has had, I hope that in the next 70 years, if you're interested, you help me think along about some of these problems. Thank you very much.
Are there questions or remarks?
How bad are those epsilons? You didn't show us any numbers. They looked awful. And when you put numbers in, what happens? How bad are they?
Oh,
sorry.
right. I was expecting that question. So they can get really bad. So the point here is that these are very pessimistic bounds, right? They have to be. And so depending on the amount of data that you have, they can be so bad that they're useless. That being said, there is, some value here. So first of all, this case here tells you that every once in a while they mean something relevant. So these epsilons are not that bad. But to us, what's really nice is that they tell us how to make, if we can make these epsilons small because we know what are the factors in those formulas. So one of the things that comes out of that analysis is that the size of the calibration set matters a lot. So if what you want to do is reduce this uncertainty, that's what you should be looking at first. That's like a first order effect. So this is something that I'm happy that we obtain, and in that way we can still control the error bounds that we get.
Thank you for the presentation. I have a question about the first result you showed. It's a marginal coverage, and it says that a probability, so probability of yk in the set, which depends on x, is guaranteed to be larger than something. So the randomness of this probability is integrating of the randomness of yx and the randomness of the algorithm. Is that right?
Right. You can integrate over the entire data. So all the training, you don't really, but sure, the training data, the calibration data, and the test data.
Okay. But it would be nicer if it could condition on the randomness of the algorithm, because there could be a random event in which the algorithm is bad, and then I don't know how to express this. You see what I mean? Like, is it possible to get the same guarantee but conditioned on the function C?
So you do need some. So the training data here is kind of irrelevant, right? The training data is giving you mu hat, but this probability goes over the calibration. So you do need the whole process, right, to get the data and redo it. I'm not sure if you can condition just on just for the test data.
Okay. And another question I have more on the practical side is, is it this algorithm you develop it and then you package and send it to every MRI user, or do you have to rerun it for every machine? Really?
No, we trained it once. So we were working with this industrial partner, so they gave us 853 exams, I think. Yeah, more or less. And we trained the algorithm there, and that way we can just put it and ship it to anyone who wants to use it, and they just have to press a button. They don't have to retrain the algorithm.
Okay, nice. Thank you.
More questions?
So, in terms of medical exams that you were mentioned at the beginning, can you explain to us what does it mean to be exchangeable and what does it mean to be beta mixing?
Well, so exchangeable would mean that the order that the exams come in doesn't really matter. So a problem here, for example, would be if you have the same pregnant patient doing the exam many, many times, let's say. So you basically have a time series, and so there's some information on how your data is happening. Beta mixing is harder to sort of justify, right? So it's a notion of asymptotic independence, right? So even if there's some dependence, as if you look at data from different parts of your data set, they don't. The dependence goes away if you're looking further and further out. That's sort of harder to understand specifically in this context, but it's really just a nice way to get some of these bounds out. The theory, you can replace this with other conditions and they would still work.
More questions?
Hi, Paulo. Very nice talk. I had a question about cross-validation. Can you use this to pick, so suppose now you have two models, can you use some of these ideas to pick the best model or something like that?
Okay, right. So usually when we're doing cross-validation, to a degree, we're interested in point predictions, right? For the test error. So this doesn't really help you with that, but you can get predictive intervals. So depending on how you think about cross-validation, if you want to pick one to be sure of something, then yes, you could. And to be honest, this literature has grown so much over the last week, whatever. It's just every day there's. I'm pretty sure people are doing cross-validation with these sorts of techniques.
Thank you.
Hello. How confined to your model? Your model can predict any stage of the development of the fetus, or you are confined to a set of, 7 months, and just you must take the RMI in 7 months and not 8, because if you do that, then the model does not predict correctly. So how confined to time is your model?
Right. So as you might have noticed, I didn't say anything about like how many weeks it's the fetus has been. So the point is, we're sort of assuming that all the information you need to predict this is in the exam. So if you have an exam from a fetus that's 3 weeks, or I guess 10 weeks long, versus one that's 40, looks very different. And so the exam is enough for us to notice this. So this covariate information doesn't add anything given the exam. So the short answer is it works for whatever gestation age that the fetus has, as long as the exam, as long as we have the exam.
Any more questions or comments? If not, let's thank Paulo again.